Have you ever stopped to wonder what actually happens when you write a line of code? It honestly feels a bit like magic, right? You type a few words and poof, a machine just springs into action. But it's not magic, it's this fascinating process of translation. And today, we're going to follow that journey from your idea all the way down to the computer's very core. And that's the big question, isn't it? We're going to trace exactly how a simple idea, something you type out in a programming language, travels through all these layers of translation until it becomes, well, a literal flicker of electricity inside a silicon chip. This is the journey that, and I'm not exaggerating, made our entire digital world possible. Okay, so this whole thing kicks off with a really fundamental problem, what I like to call the human-computer gap. See, we think in abstract ideas, in logic, in words. Computers at their heart only understand two things, on or off. I mean, we're talking about two totally different worlds here. At its core, every single app you use, every game you play, it's all just a computer program. The best way to think about it is like a super detailed recipe. The computer is the chef, and it follows every single step blindly, but with absolute perfect precision. The whole art of programming is just crafting that perfect recipe. So to really get a grip on this gap, we first have to understand the two sides. On one hand, you've got the hardware, the physical stuff, the silicon brain and metal body of the machine that you can actually touch. And then you have the software. You can think of it as the ghost in the machine, the instructions that tell all that hardware what to do. All right, so let's talk about the hardware side of things. What is the native language of the CPU, the actual brain of the computer? Well, I'll tell you, it's not English, it's not Python, it's not any language we'd recognize. No, it's something way more primal. Well, this is it, machine language. This is, and I mean this, the absolute rock bottom of computing. Every single action a computer ever takes, from displaying a letter on your screen to calculating a number, has to be broken down into this stream of ones and zeros. It represents simple electrical signals, on and off. This is the only language the CPU speaks, period. I mean, just look at this. This is a real instruction in machine code. Any idea what that's supposed to do? Don't worry, me neither. Now, can you imagine trying to build a modern app using millions, maybe billions of lines of this? It's basically hostile to the human brain. So you can see the problem, right? The early programmers faced these enormous challenges. Not only was writing in machine code incredibly tedious, but a program you wrote for one type of computer just wouldn't work on another. Every single family of CPUs had its own private language of ones and zeros. Something better had to come along, and fast. And this led to a really simple, but honestly brilliant idea. What if we just created a more human-friendly dictionary for machine code? This idea gave birth to something called assembly language, and it was the first real bridge across that human-computer gap. And that's where assembly comes in. The concept is super simple. Instead of using those raw, awful numbers, let's use short, memorable names, we call them mnemonics, for each machine code instruction. It's still a direct one-to-one translation, but man, it makes a world of difference for the person writing the code. And you can see that leap in clarity right here. That cryptic string of ones and zeros becomes move al 0x61. All of a sudden, there's a verb, move for move, and things that kind of look like names. It's still super technical, but for the very first time, it's not just noise anymore. But, assembly was still what we call a low-level language. It was just a thin layer sitting on top of the hardware. You still had to know all the tiny details of the CPU, and your code was still totally locked to that specific computer. It was a step up, for sure, but it wasn't the final answer. No, the real game changer, the big revolution, came when we just stopped trying to think like the machine. Instead, we started building languages that let us programmers think like humans. This was the dawn of high-level languages. And the magic word here is abstraction. High-level languages create this amazing, protective layer that hides all the messy, complicated details of the specific hardware. This lets a programmer work with words and logic and math in a way that just makes sense to a person, not to a microprocessor. And boom, this slide just lays it all out. We go from that indecipherable binary to a technical but readable command to a simple, clean statement. A equals 97. I mean, anyone can look at that last one and get the gist of what's happening. And that right there, that's the whole ballgame. We've moved from telling the computer the microscopic how to simply stating the high-level what. I mean, the benefits were just huge. All of a sudden, programming became faster.
It became easier, and way more people could learn how to do it. And maybe the most important part, programs became portable. You could write code once, and then with the right tools, run it on completely different kinds of computers. This changed everything.
Okay, but wait. This leaves us with one last mystery, doesn't it? If the CPU only understands that crazy machine code, how in the world does it run our beautiful, easy-to-read, high-level code? Well, this is where the translation magic comes back into the picture.
Well, the answer is, you guessed it, another program, a special kind of translator. Its only job in life is to take our human-readable code and meticulously convert it all the way back into that stream of ones and zeros that the CPU actually understands. And it turns out there are two main ways this translation can happen.
First up, we've got compilation. Think of this like translating an entire book from English to French. A program called a compiler reads all of your code from top to bottom, translates it all at once into a complete machine code version, and then packages it up into a standalone file, an executable. You can then just run that file directly, and it's usually super fast.
And the other way to do it? That's called interpretation. This is way more like having a live human translator whispering in your ear. An interpreter program reads your code one line at a time, translates just that single line into machine code, tells the CPU to run it, and then moves on to the very next line. It all happens on the fly as the program is actually running.
So what's the difference? What's the trade-off here? Well, compilation happens all up front, and it creates a highly optimized and really fast final program. Interpretation is more flexible, translating as it goes. That's why languages like C++ are usually compiled for performance, while a lot of web languages like JavaScript are often interpreted for flexibility. They're just two different strategies to get to the exact same goal, bridging that final gap.
And really, that's the whole story. It's this incredible journey of abstraction, of building these layers of language one on top of the other, creating this sophisticated bridge that allows our human minds to communicate incredibly complex ideas to a hunk of silicone that only understands on and off.
You know, this whole journey we've been on has been about one thing, building more and more layers of abstraction to make it easier for us humans to talk to machines. And that leads to a final, pretty fascinating question. As our tools get even more powerful, even more abstract, from drag-and-drop interfaces to AI that can actually write its own code, where does this journey end? Will we even need to code in the future, or will we just talk to our computers and tell them what we want? Something to think about. Thanks for joining me on this explainer.